Okay, so free body diagram of the whole thing doesn't change. So we have the 750 and then the force and the couple over here. The free body diagram of member 1. We have the force and the couple here. We have the force on 1 by 2 here. And over here, we have the force on 1 by 5 and the force on 1 by 3. Any questions about that one? And then number 2, we have the force on 2 by 3 and the force on 2 by 4. That's because at C, the pin is part of member 2. And down here, we have the force on 2 by 1. And then number 3, since the pin isn't part of member 3 at C, all we have here is the force on 3 by 2. And then at D, the pin is part of member 1. So all we have here is the force on 3 by 1. And then number 4, we have the 750 newtons. At C, the pin isn't part of member 4. It's part of member 2. So all we have is the force on 4 by 2. At E, all we have is the force on 4 by 5. And then for member 5, the highest numbered member never has any pins connected to it. So all you ever have on the highest numbered member is, well, any external loads on it, and then the forces from other members are just coming from the pin. So we have the force on 5 by 4 here, and the force on 5 by 1 here. Oops. Okay, and so notice that these free body diagrams look totally different. So member 1 here is member 5 in the other case. This one has 1 force at the top, 2 forces at the bottom. This one has 1 force at the top, 1 force at the bottom. And as you go through, I mean, that's going to be the case with several of these. Depending on the numbering, it's going to look different. But at the end of it, once you calculate your values, and you're going to get different values for things too. It's not just renaming forces. So you're like, how is that the same answer? But if you go back with your answers and redraw your free body diagrams with numeric forces in there, and add up any forces that are acting at the same point, what you end up with is all 5 of those members having the same total external forces on it. And that's what matters. Like, that's what determines the internal loads and things like that. Okay? Yep.
I have a general question. You were saying before that we could, as we go through it, each step, we could change our output.
Yes.
So let's, in a general fashion, let's say you did a calculation with that moment about point,
Mm-hmm.
and then you were using that same member in your next set. You
Mm-hmm.
have to choose the same about point. You can use that about that.
This MR.
Yeah.
Okay, that MR is a couple. And so it doesn't matter what the about point is.
Okay.
So that MR, yep, so it doesn't matter. I mean, basically just think of it as like you're just looking for a bunch of equations that are true. And so using one about point, you come up with equations that are true. Using a different one, you come up with equations that are true. And so those work fine in a system of equations. Yep.
Can you change the origin?
You can change the origin. The only reason, in a way, you shouldn't, like, to me, this doesn't make any sense to say this, probably, but like, you probably shouldn't change the origin. But the reason that it works out fine is forces don't depend on origin location. They only depend on direction. Same with couples. And so, like, if you were doing calculations that depended on position or something that does depend on the origin, then you couldn't switch the origin. We can, because as long as you don't change the directions of the axes, you get the same thing.
Keep one origin.
Yeah, you can keep one origin or you can move the origin. What you can't do is change the orientation. Yeah.
Here on number 4, your solution, you pick different.
Oh, yeah.
And
Yeah.
And your A,
Uh-huh.
your A is the same.
Right. Well, if you ever forget what you're allowed to do and what you aren't allowed to do, of course you can always keep the same origin and same about point through a whole problem. But
It's easy to keep the same origin for every member. Or does it matter?
Yeah, doesn't matter. So if it's just as easy, then keep it in the same place. But if it helps you out a lot, then yeah, you can move the origin around. Any other questions about this? Actually, if once you get through all these problems and you're looking for more stuff to do to make sense out of it, if you get to that point, I think it would be a great exercise on 3 or 4 to renumber those bodies, redo the calculation, and make sure that when you go back and find the external forces on all the members, that you get the same thing. If you didn't, that would be a problem with the method you're using, Any other questions about practice problems or anything about the test tomorrow? Okay. Okay, so last time we started talking about internal loads. And I brought up a problem where we had a beam with 500 newtons acting down there, 500 acting down there, and 1,000 up here. And at a distance of 0.25 meters, we wanted to calculate the internal loads. and we used a coordinate system. Yeah, so the coordinate system was oriented like this, and our about point was here. Okay. So now I'm going to do this calculation again, but I'm going to, so instead of going from the left side and making our cut, I'm going to go from the right side and make the cut. It's sort of arbitrary, right? If an internal load is a actual thing, you should be able to calculate it from any direction you want. The only concern is that the coordinate system stays the same. We're going to keep the same coordinate system. So last time we worked from the left side. And we got an internal force vector of 0,500, and a internal couple of negative 125. This is newtons, this is newton meters. Okay, so working from the right, we should get the same thing. So our free body diagram looks like this now. It doesn't include the point A. But it includes this and this. This distance was 0.75. So now we have .75 there. And I'm going to use the about point over here this time. So Newton's second law, oh, and this isn't complete yet. We have those internal loads. That's what we're trying to calculate. We're assuming that, again, it's a fixed joint between what we are including and what we're not including. I think last time I drew it in here, like, just so you remember, like, this is what we're doing. We're skipping the dotted part, and the part that we're isolated is in the solid outline. And so the force applied by the material that we're skipping is this, and it's a fixed joint, so we also have a couple, M. So Newton's second law says Fx, Fy plus 0, 1,000 plus 0, negative 500 is equal to zeros. That tells us that the force vector F is equal to 0, negative 500. And the rotational equation says, this is the about point, so there's no force produced, no moment produced by the 500 Newton force. There is a moment produced by the 1,000. What's that moment? 500, and it would, about A here, would make it rotate clockwise, so it's negative. So negative 500. And then Fx wouldn't produce any moment, but Fy would produce a clockwise moment of 0.75 Fy. So minus 0.75 Fy is equal to 0. And so, whoops, and I end the moment too. Okay, so we have the couple M, we have the moment produced by the 1,000 Newton force, we have the moment produced by the force Fy, and those have to equal 0. And if you do that calculation, you get that, so put negative 500 in for Fy, you get 375 positive, and so you get negative 125 for all the constants, and so M is equal to positive 125. What? The origin, since all we're doing is talking about is, well, we're talking about forces, row vectors, which is displacements, and couples. Those don't depend on the origin, so I didn't even really specify. If you were going to fill out the table, you'd have to choose an origin, but what does matter is the about point, and that's over here at the right. Should we fill out the table for that? We could. Okay. Okay. So when I do it as a shortcut like this, the way I think about it is there's a hinge at your about point, okay? And this thing, so we're imagining everything rotating about the about point. So what kind of rotation would this 500 Newton force cause? None, because it's right at the joint. What about this 1,000 Newton force? That would make it rotate clockwise around A. So we know that's going to be a negative moment. And the magnitude is going to be 1,000 times the moment arm, which is the distance from A to the force. So that's just sort of a shorthand way of thinking about the row vector. So the row vector, because we have all the forces perpendicular to the row vectors, it's just a multiplication. But if you filled out the table and did it all as cross products, you'd get the same thing. But if you're not comfortable with that, you can always fill out the table. You know, it's just a rigid body problem. So you could choose an origin, calculate the row vector, take the cross product, and it works just the same. Okay, so the bottom line here, this is something that's a problem. The internal force that we got cutting from one direction was opposite the force from the other direction, and the same with the couple. And that direction, like which direction you're working, should be totally your choice. I mean, we're trying to calculate something that would be the same as long as you use the same coordinate system. So what's going wrong here? Why don't those match? Anybody have intuition about that? It's not the about point. We could have used the same about point and gotten it. It just seemed... no, so all that's not the problem. The problem is when we cut from the left side, we were calculating the force on this short piece by the long piece. And when we cut from the long side, we were calculating the force and couple on the right piece, the long piece, by the short piece. So they should be equal and opposite because it's Newton's third law, okay? So the question is how to deal with that. We can't be talking about values that are going to be different depending on which side we cut from. So these are equal and opposite. Because of Newton's third law. So how can we change the calculation approach so that we get the same thing no matter which side we go from? So we need a sign convention that gives the same values from either direction. And so the way we're going to do that is instead of thinking of the force on the left by the right, and the couple on the left side by the right side, or the other way, you know, the force on the right by the left and the couple on the right by the left. We're going to think about cutting out like an infinitesimal sliver, okay? So we're not just talking about a surface anymore. This would be talking about a surface that separates the left from the right. We're instead going to be investigating just a thin little sliver right at that boundary point. So investigating the loads on an infinitesimal sliver of material at the boundary. And so if this is the whole thing, we have 500 acting down there, 500 down there, 1,000 up there. And instead of looking at this surface, okay, we're going to look at a volume of material, infinitesimal, but it actually has a volume with a left side and a right side, okay? And if you blow that up, so what we have, so now the way to think about what we had before is when we isolated the left side, we had a force of 0,500. So that means that when we investigated the left side, this is a little confusing, but we were looking at a right surface. Like we were looking at a force on a surface that where the material was to the left and the gap was to the right, okay? And so, and we got a value of positive 500. So we had a value that looked like this. Okay, and when we did it from the right side, we were looking at the force on a surface that faced the other way, and we got a value of negative 500. So we got a value like this. And if you look at the couples, when we isolated the left side, we had a moment that was clockwise. So we had something going this direction. And when we investigated isolating the right side, we had something like that. And notice that, what?
The reverse.
It's the reverse. We had
First one, negative 100, 125.
negative 125, so that's a clockwise couple. So that should be right, I think.
This one we got positive 125.
Okay, so think about like when we isolate the left side, we're okay. So when we isolate the left side, and here's the sliver of material, we're looking at the loads acting on the right face. And when we investigate from the other direction, there's the sliver. We're looking at the loads over here. So the first way we did it gave us the values.
It's the first one is one. We got 125, negative 125.
Negative 125.
So direction is clockwise.
Clockwise.
Yeah.
So that says that, so we got clockwise over here, and a positive force like that. And then going the other way, we had a negative force like this and a counterclockwise couple. And look at where the rectangle sits in there.
Yeah, but you did it in the big section, in the reverse.
In this?
Yeah.
But see, the way I have it, like, now look at the relationship between these loads compared to that red rectangle. That's what I mean. And so you have an upward force and a clockwise couple on the right side of that sliver. You know what I mean?
Yeah.
Okay. So that's why it's sort of confusing. Like working from the, if you're working from the left, you're really calculating loads on the right side of that sliver. And if you're working from the right, you're really calculating loads on the left side of that sliver. Okay.
To be clear, the left side sliver will rotate clockwise.
The
Left side sliver.
One and two.
Yeah.
yeah, so just notice this. Like if we isolate the left side of the cut, okay, then what we're calculating is loads on the right side of the sliver. Okay?
Okay.
And if we're looking at the right side of the cut, then we're calculating loads on the left side of the sliver. And so so I know that's confusing, but that's
Okay, I get it.
okay.
Because of it's a cut piece.
Yeah.
Sliver.
Right, right. And so, anyways, if you look at this, you can see that what we have here is a sliver that's in equilibrium. You have a upward force of 500, downward force of 500. You have couples that balance. These are both 125. And so we need to think of what's happening to the sliver and not what's happening to the surface. Okay? So the sign convention comes from what happens to the sliver, not what happens to the surface that's cut. So that means that what right now we would call positive 500 for this one and negative 500 here, right? And we'd call this negative 125 and this positive 125. Now we want to call those the same thing because they're just two ways of describing a single sliver in equilibrium, okay? If this side is up, this side has to be down. So we want to decide to either call that this setup positive 500 or negative 500. Okay, so here's our sign convention. So first, we'll talk about the internal tension. If your sliver has a loading pattern like this, that's positive. And if your sliver has a loading pattern like this, that's negative. Right, yep, that's right. And the second thing we'll talk about is the shear force. We didn't have any internal tension in that example I just did, but we did have shear force. So if your sliver looks like this, that's called a positive shear force. And if it's the other way, it's negative. And then the last one is bending moment. And if you have a bending moment like this, that's positive. And the other way is negative. So, yeah.
Is there some sort of logic for the shear force as to why it makes sense to convention?
Yes. Not that I can think of. Yeah, I mean, it seems like the other ones, the way the other two are is if you're working from the left side, positive coordinate system values give you positive internal loads. And yeah, this one is backwards of that. So I don't know why that is. As far as remembering them, these two you're kind of on your own, but I can help you remember the sign convention for the moment. A positive bending moment tries to make a beam look happy, you know? Because I'm happy. Okay, so that's a positive. Obviously, that's positive. And that's negative. Okay, but you have to remember the other two. All right, so what this means, I said this a minute ago, but what it means is if you're working from the left, then you're dealing with the right surface. And so a positive internal tension is a horizontal force pointing to the right. And if you're working from the left, a positive shear force is down. and from the left, a positive bending moment is counterclockwise. In this class, we're always going to work from the left, but I did want to give sort of a sense, like I think it can be really confusing why would you mess with the vector sign conventions? Why do we give it these new names, and why does the shear force, a positive shear force, point down? And the answer is that we're not talking about forces acting on surfaces anymore. We're talking about deforming loads on a sliver of material. Okay, so let's take a 10-minute break, come back at 2:16, and I'll start going through some examples.